today we're going to talk about variance and standard deviation. So before today, we only had a couple of ways to see how spread out data was. So our ways, our very basic way was range. That was just minimum minus maximum. A little better way was interquartile range. That was Q3 minus Q1. And that was it, really. So variance and standard deviation is a much stronger way of figuring out how spread out data is. And we're going to learn how to do this by hand. And so that's what today is going to be about, and then we're going to practice it ourselves. And so this is 14F in your packets. So this is the formula for variance. So I'm going to zoom in on this a little bit, and I'm going to explain what all these values and all these symbols mean because they are kind of confusing. So X bar, X with a line over it means mean. That's a value you're very comfortable with. This S squared means variance. So this whole quantity means variance of n values. So n just refers to the number of values we're counting up. So if we're counting up 10 different values, it would be S sub 10. Squaring it is just what variance does. Does anyone know what this kind of Greek symbol means here? So sum, yep. So this says we're going to add up the first data point, that's I equals 1, to the last, that's I equals 1 to n, of, and xi refers to all the individual data points, xi minus x bar. So we're taking all the data points. So let's say we were looking at all of our shoe sizes. We would take everyone's individual shoe size and subtract it from the mean. We'd square them. We'd add them up. And we divide it by the number of people there were. And so that's, we'd square them. Oh yeah, we'd square it. And that is the variance. And there's a neat little table that's used to calculate variance. And so that's what we're going to be using, bless you, so that we can really organize our data here. So for those of you that rely on the graphing calculator to tell you the answer, that's not going to be super helpful because I'm going to be requiring you to show your table in order to show your work. Now, the more popular measure than variance is standard deviation. It's more widely used because it corrects for the fact that we don't really need to have all of these be squared. And so the difference between the variance and the standard deviation is the square root of all of them. So what we're going to do in class today is practice calculating the variance and then the standard deviation. So what we're going to do is poll ourselves on what our shoe sizes would be if we all had male shoe sizes. And the reason we have to consider male shoe sizes is because we know that if we were to all go to the shoe store and we would tell the person what shoe size we need, if we said male and female, that wouldn't be the same size. So what we're going to do is to create a table. So let's do that on our papers. And the first thing we have is X. X is just our data points. So in other words, our shoe sizes. So X, going to actually give ourselves a little room and write comma, shoe sizes, and we're doing male. So as if we were buying in a male shoe size. Okay, so Michael, what's your shoe size? Michael Boucher. Oh, so you can do 10 by 5. 10? Okay, so yes, I know. If you were to buy, do you know how to correct for male? You're subtracting 1.5.
But I've used like 6 for my shoes.
Yeah, so we'll say 6.5. Okay. Okay. Wow, 10 feet. All right, Aaron.
13.
13. Michael Schaefer.
10.
Malik.
4.
Gabby. 7. In women's?
No.
Men's? Okay.
I think it's a 10.
Okay. And you said 12, Malik? Okay. I think I got distracted. My fault. And Gabby, you said 7? Okay, Zoe?
6.5 or 6.
Okay. Armand?
12.
12, and then I would be an 8. So first thing we do is we write down our data. So we're all going to want this in our notes so we have an example. So X is just our data. Now what we have to do is calculate the mean. So what I'd like you all to do is calculate the mean of the data. Okay, so we got one person saying 8.8. If we could confirm that, then we can move on. Wait a minute. Cool, good. So now you're going to write X bar equals 8.8. Remember, X bar is our mean. Okay, next column is X minus X bar. So you are going to take every value and subtract it from 8.8. So this is where, how far we're deviating from the mean, standard deviation. So you do 10 minus 8.8. Some of these will be negative, and that's okay. Yep. So again, it's the value minus 8.8. So you're below the mean, it's going to be negative. If you're above the mean, it's going to be positive. So I want to make sure everyone's copying this down. Okay, the next part of the table is you're going to square all of these quantities. Now, when you square the quantities, what happens to them? They become what? Yeah, bigger. Most become bigger, and they're all going to become positive. So just keep in mind, you'll end up with all positive quantities. So someone could start at the bottom of the list, someone could start at the top. We're going to square all the quantities. So yeah, you're going to want to copy down everything. And just make sure this column is all positive for you. So when you put in that you're squaring it, you don't even have to account for the fact that it's negative. Because when you square it, it's going to end up being positive. Anyone get the 1.8 yet? .64. All right. Now remember that little Greek symbol there? What did it stand for again? Sum. So now we have to add them all up. So that's that Greek symbol. It's a capital sigma. It stands for sum. So I guess I didn't need to make these lines so big. We're going to add them all up. So a couple people would do that sum so we can compare answers.
.06.
56.06.
86.06.
Anyone else get that? Okay.
Oh, I think it is 86.1.
Okay, so here's our sum. Do you remember what we do next then in the formula? What we do next in the formula? Yeah, and what does N stand for? Yeah, number of people. So we have to count up the number of people we surveyed. 10? Divided by 10, so that's 8.61. And then if we're finding the standard deviation, what do we have to do with this?
Compared to the average.
Well, by subtracting it from the mean, that's that part of it.
Yeah.
So what we have to do for standard deviation is take the square root. So it's 2.934 is our standard deviation. So that's S sub 10 for these 10 people, we have a big deviation. So that means our shoe sizes are not very standardized in this room. Hence the, Aaron to Katie, that's a big deviation of shoe size. So.
Well, we are not all male.
True.
Oh.
I think big realizations happening in here. I have a feeling they have nothing to do with math, but that's okay.
We're using this as male shoe sizes, but we're not all male, so the lower
right, and males have bigger feet. Okay, so if the data is very symmetrical, this is what happens. If we have symmetrical data, what was the value of a standard deviation? One standard deviation, what did we get there? 2.6? Okay. It would mean, and what was our mean? 8.8. A shoe size of 8.8 plus or minus 2.6. So can someone do 2.8 plus 2.6? Oh, let's go back.
Is it not 2.9?
Oh, 2.9. Come on.
Oh.
Yeah. Okay.
Nice try.
Okay, 2.9. Okay, so 8.8 plus or minus 2.9. So that's a shoe size of like approximately, if we add the 2.9, what do we get here?
That's 89.
8.8, that was our mean, right?
11.7.
11.7. And then how about if we subtract, what do we got?
5.9.
5.9? Okay. That means if our data is very standardized, that means 68% of our people will have a shoe size between roughly a 6 and an 11.5. If our data is very symmetrical, like the standard bell curve. Heights are very symmetrical. The more people you have, if it's just standard people, not like people on a basketball team or people on a gymnastics team, those heights are not symmetrical. They tend to be very bell curvy, grades are not. But this is how it works. One of these are one standard deviation, what we just calculated. Our standard deviation was 2.9. The mean is right in the middle. It's at the 0, or 8.8, a shoe size of about 9. And one standard deviation is plus 1, minus one standard deviation is minus 1 from that. And if you have what is called a normal curve, you get 68% of your population within one standard deviation. And that is how statistics work for normal curves, for a very symmetrically distributed curve. All right, so.
So which one was for that?
What's that?
Which one was for that?
So if our data was pretty in the middle, which, I don't know, I'd have to graph our data on.
Because how can you even do that?
So if we were to go out a little further, like continue to add the 2.9, because, so for us, one standard deviation is about 3 shoe sizes. So if I go out another 3 shoe sizes, it would include 95% of the people on here if we had very symmetric data. Yeah, it's pretty complicated. And the more people we surveyed, like if we had the whole school in here, it would make a little more sense. I think it's hard because we only have 10 people that we've surveyed. But what this says is that roughly 68% of us fall within a shoe size of 6 to about 11.5. if the data is really symmetrical. So if we were to do a little histogram on it. All right, so let's look at this example. A library surveys 20 borrowers each day from Monday to Friday and records the number who are not satisfied with how much reading material there is. The results are 3, 7, 6, 8, and 11. In the following year, the library receives a grant that enables the purchase of a large number of books. And this survey is repeated, and the results are 2, 3, 8, 4, and 6. Analyze each set of data by finding the mean and standard deviation. What do the statistics tell us? So mean and standard deviation for the first, mean and standard deviation for the second. I feel like I want to assign half the class the top, half the class the bottom. Are we ready to do it? Do we want to do one together?
I think we can do it.
Okay. Okay, thank you for everyone that went to the board. Let's do a bit of a compare and contrast to what happened one year versus the other year. So it looks like initially we had a mean of 7 people unsatisfied with a standard deviation of 2.67. So this was our mean, and our standard deviation was 2.67. And then our next mean was 4. Okay? And then standard deviation looks like we got a sum of 10. And then what do we do after we find the sum? 1, 2, 3, 4, 5. And then square root. So our standard deviation is about 1.41. So what do the statistics tell us about how pleased people are with the reading material? Are they more pleased? Yeah, because we have less people complaining. And then this means, the data was less spread out because the deviation was less. The lower deviation, the more concentrated the data. So here, the more spread out the data is. Questions on that? Okay, so you have that table which describes the whole process here, which is finding the mean, subtracting it from each data point, squaring it, dividing it by the number of data right here, and then taking the square root, and that tells us how spread out the data is. All right. Any questions? All right, so we're going to do this on Monday.